Yeah, thank you everybody for being here. I'm in the weird spot of being also the speaker here, but yeah, please forgive me. I'm here to present some joint work with Dominik and with Ariel on randomized apportionment. Some of you might know what apportionment is, otherwise all of that is going to come in the next few slides. But I just also want to start on a personal note and say that I'm really fond of this work. I think we started out chasing a question that was more esoteric than anything else, but we ended up with some mathematics that I find satisfying that also go beyond the specific questions we asked. And we ended up learning some things not just about randomized apportionment, but also about deterministic apportionment. And I hope you'll get a bit of a flavor of that throughout this talk. So what is apportionment? I will start with the classical deterministic setting. Apportionment is the process that comes before the redistricting that Wes was talking about. Namely, we have this number of seats in total in the legislature. Here, 100 seats represented by 100 little gray squares. And we need to somehow divide that up over the states that form our country. Here on the left, there's an example country consisting of 3 states, each with a population of 1,000. And so these are the states that we need to divide the seats among. And the overarching goal is always proportionality. And so because every state has 1/3 of the total population, the goal of apportionment would be to give 1/3 of the seats to each of the states. Now, many of you have probably spotted that 100 is just not really divisible by 3. And so we somehow need to deviate a bit from that. And so, for example, we might give 33 seats to the brown state, 33 seats to the orange state, and 34 seats to the beige state. And in some sense, deterministic apportionment is all about managing these necessary deviations from proportionality. The mathematical construct being studied that makes these managing decisions is what we call an apportionment solution. And that's just a function that takes in this vector of populations, that takes in the desired house size, so the size of the legislature, and then returns another vector that says how many seats each of the states should receive. And this is you might think that there's not really much to study there, but there's many different apportionment solutions that have been proposed. And to try to argue that one is better or one is worse than another, we do the typical thing in social choice, which is to develop different axioms. And by far the most prominent axioms are these 3 here: quota, house monotonicity, and population monotonicity. I'll go through them. So quota says that a state's number of seats should be either the floor or the ceiling of their proportional number of seats. So before, each of the states deserved 33.333 seats, which means that any solution that satisfies quota can't give any of the seats less than 33 or more than 34 seats. The second axiom is house monotonicity, which says that as we increase this house size, say from 100 to 101, none of the states should lose any seats. And then finally, there's population monotonicity. It's a bit more cumbersome to state. It does feature quite prominently in our paper, but not in this talk, and so I will spare you the definition. Instead, what I would like to say is that this field really has elegant mathematics and a lot of political drama. So there's this whole mathematical theory mostly developed by Michel Balinski and Peyton Young. And what is really special for our field is that a lot of the discussion between apportionment solutions and the axioms has not been an academic debate, but instead in the 1800s, the who is who of American politics has worked very hard to convince people to use their apportionment solution and has pointed out violations of these axioms in order to argue for that, and very often in a very self-serving manner. So these solutions advocated by the specific people tended to, by accident, also favor their own state. So it's incredibly entertaining if you ever have the time. I can only recommend looking into this. So far, I've talked about deterministic apportionment. And I've said that in deterministic apportionment, we try to manage these necessary deviations from proportionality. And that's only natural in this deterministic setting. You can't give a state something between 33 and 34 seats. But in this room, many of us are computer scientists, economists, mathematicians. And it's very natural, I would argue, to think, well, maybe we can use randomness to get this proportionality perfectly, at least in expectation. This is exactly what a mathematician called Geoffrey Grimmett has proposed in 2004. And the way that he thinks of apportionment now is that an apportionment method is a function that takes in a population vector, that takes in a house size, and then returns a random variable that ranges over these outcomes. And this allows the random variable then can break these ties in different ways. So for example, here sometimes the 34th seed goes to beige, sometimes to orange, sometimes to brown. And this will allow us to get this kind of proportionality. Grimmett did propose one specific apportionment method, and he argued in its favor using these two axioms, ex-ante proportionality and quota. Ex-ante proportionality is the proportionality that I've been talking about all along. So a state's expected number of seeds should exactly equal its proportional share. And then also quota is satisfied. So for any of the outcomes ex post, any of the outcomes in the support of the random variable, their quota should hold. And we like this. We're building up on this. We think it should have gotten more attention. But we also think that there really remains a bunch of work to be done. And the reason that we think so is that these two axioms together are not discriminatory enough. There are many, many different ways of building apportionment methods that satisfy these two methods. I won't really go into a lot of details here, but in essence, guaranteeing ex-ante proportionality and quota turns out to be pretty much equivalent to something called probability proportional to size sampling, or PIPS sampling, in the statistic literature. And I've taken some screenshots from this book in the 80s, where they literally give a table of 50 different methods that all satisfy the properties of PIPS sampling. And so you can turn any of them into a different ex-ante proportional and quota apportionment method. So what should we do? We should somehow further narrow down what an apportionment method is. And for that, we turn to additional axioms, and specifically to these oldies but goodies of house monotonicity and population monotonicity. It's actually a bit subtle how you would apply these kinds of axioms to a randomized setting, because they compare the outcomes in an apportionment solution originally across different population vectors or across different house sizes. So the inputs are different. And now in Grimmett's setup, the result of one of these inputs is something random. And it's not really clear how we would apply this relational axiom to compare different outcomes if this randomness is in the way. And in some sense, we do something that I think is quite natural. We, in some sort, couple the randomness between different inputs. Or another way to think of this is that from now on, an apportionment method is formally a random variable that ranges over apportionment solutions. So in some sense, we at the beginning choose some randomness. Then from then on, the mapping is deterministic. We have a deterministic algorithm, if you like to think of it that way. And overall, this gives us a randomized algorithm. And because the randomness is out here, we can still totally compare what happens for different inputs. And yeah, so we can still argue about ex-ante proportionality. That's just as defined before. As before, we can argue about quota. But now we can, for example, say that an apportionment method is house monotone if all the solutions in its support are house monotone. Speaking of which, I will now talk about our main result, which is an apportionment method that satisfies ex-ante proportionality and quota, the two axioms of Grimmett, and in addition, house monotonicity. Getting any two of these properties is not too tricky. So for example, if we only wanted ex-ante proportionality and quota, we could take Grimmett's method, or we could take any of these PIPS sampling things. If we only wanted quota and house monotonicity, nothing would really force us to be random at all. And so we could lean on the literature in deterministic apportionment, which in particular still has a complete characterization of these apportionment solutions satisfying these. And we tried really hard to go from either of these two intersections into the middle and get the third property as well. And that was really hard, and we did not get there. So the way that we eventually did it was from the third direction, namely from a way to get ex-ante proportionality and house monotonicity. Specifically, I would summarize this as sampling with replacement. And I will quickly tell you what this is about, and then how we go from there and add quota in addition to that. So OK, we want to get ex-ante proportionality and house monotonicity. And I will now peel away a lot of the complexity that I built up before with the random die and all these distributions. So don't worry if not all of that was clear. So I will promise you that for the purposes from now on, we can kind of ignore the interdependencies between different population profiles. So we will just treat this one as fixed. And what we really want to do now is just randomly build a sequence of outcomes for all the different house sizes, for how h equals 1, h equals 2, h equals 3, that is monotone. So we keep adding more seeds, we never take any away. And there's a very natural way to construct this. which is that we just go through the different seeds. So this is the first seed, this is the second seed, this is the third seed. And for each of them independently, we choose which state should receive that. And we do that with independently and with a probability proportional to the population. So for example here, let's say that we flip we roll the dice, and this is the outcome. So the first seed goes to orange, the second seed to orange, and the third seed to brown. And then, for example, if we query this apportionment method in the end, and we have a house size of 3, we will say that 2 of these 3 seeds go to orange and 1 seed goes to brown. And if we construct this method in this way, then we immediately get house monotonicity by construction. We do get ex-ante proportionality, which comes from this proportionality in every single decision that we make. But we do not get quota at all. And in fact, you can see this here. So for example, for h equals 2, we give both seeds to orange. But the orange state only deserves 0.6 seeds. So by quota, we can't give the orange state more than 1 seed, and we give it 2. So we've already violated quota. And there's no reason why we wouldn't, because we made all these decisions independently. So it really seems like there should be some way of plugging these together. And I have this very visual metaphor in my mind of plumbing between them, which only makes sense once you've seen a lot of the theory that I tried to somewhat hide. But somehow, the decision, for example, to give the first seed to the orange state is perfectly fine. We will have to do that. But when we do that, that should somehow take away from the probability that we will also give the second seed to orange. It should add some probability to the fact that then in the second seed goes to brown, because otherwise there's another way in which we are already violating quota. And it turns out that there is a way to do exactly this, and a way that somehow does justice to this plumbing metaphor. Specifically, we use pipage rounding developed by Gandhi et al. And so we have this fancy graph here. And so these edges here, this is a bipartite graph, even though it doesn't show. These edges are weighted. And we will do some random rounding and get a matching on this graph. And in the end, which of these edges get rounded up will appear in the final rounding. This will tell us where each of the seeds goes. You don't have to follow along. I'm sorry, this is all very quick. But by having this intermediate structure here, and by using this pipage rounding procedure, what we do to round this matching is that we repeatedly find cycles in this graph. And this is just one example cycle. And one example thing that we might do with this cycle, where we add an amount to every even edge, and we decrease the weight of every odd edge. And here, maybe just vaguely you can follow along, that we're still able to increase the weight of the orange edge. So we're inching towards giving the first seed to the orange state. But we're immediately paying for this by taking away weight from giving the second state to the orange, second seed to the orange state, and adding more weight to giving the second seed to the brown state. And so everything slightly magically ends up working out, and we're able to guarantee house monotonicity, ex-ante proportionality, and quota. What is this good for? So I'm zooming out again a bit from all these graphs. As I said, we've narrowed down what an apportionment method might be in this randomized setting. But beyond that, there's some nice things that fall out. So for example, we now have a characterization of these deterministic solutions that satisfy quota and house monotonicity as the vertices of a matching polytope. You don't have, maybe you see that immediately, maybe you don't, but this is kind of nice, and it's a very different characterization to the one that was in the literature, and it tells us something about deterministic apportionment. Another thing, if you happen to know about this, in some sense, house monotone apportionment methods or solutions are the same thing as picking sequences in weighted fair division. And there's this work by Chakraborty et al. That shows that the quota property that we satisfy is sufficient for a fairness property there in fair division called weighted proportionality up to 1 good. I also want to say, and I don't think I have time to really step through this in as much detail as I would like, that this plumbing construction of using pipage rounding and correlating what we do in different copies of the same graph ends up being much more general than just apportionment. And specifically, for any bipartite graph that you can apply pipage rounding to, we're able to add this plumbing and to augment this process in a way that still satisfies all the properties that pipage rounding satisfies. I will zoom through these. And in addition, satisfies a new property, which we call cumulative degree preservation, that is sort of the equivalent to quota. So it tells us something about what happens in the first two copies of this graph jointly and what happens in the first three copies of this graph jointly. And yeah, we propose some applications of this in social choice and fair division settings, but we're also very interested in exploring where this might have applications in algorithms, because pipette rounding has been a very popular technique there. Okay, to wrap up, what did we do in this paper? We proposed this, this extended setting of a randomized apportionment. And we developed an apportionment method that satisfied these three properties of anti-proportionality, quota, and house monotonicity. We also developed this generalized technique for like pipette rounding, which we call cumulative rounding. And our paper also includes results for population monotonicity. There's a classical impossibility that we strengthen that tells us more about deterministic apportionment than was known before. And we also give an apportionment method that satisfies population monotonicity and ex-ante proportionality, but not quota. And this is, like, again, very cute, and it's based on Poisson arrival processes. Then finally, I would just like to give a shout out. I think a lot of like work remains open, and I think we need more axioms for randomized apportionment. Whether house monotonicity is exactly the right thing to do, I don't know. Plausibly, but I think there's a very wide space of other axioms that you might want to explore, and I'm very interested in this. And in fact, Jamie Tucker-Falls here and we've started thinking about this. And for example, one very natural axiom to us seems something like saying, if a set of states S, if all of them grow in population and all the other states shrink in population, then not only should the marginal probabilities of the states in S grow larger, but somehow also the correlations. We should be more likely to give all of them the ceiling rather than the floor. And this is a problem that has kept us busy for a lot of months now. We've tried very hard, and if you have any hunches or like know anything that seems relevant, we would really love to talk, so please reach out. Yeah, thank you so much. Please ask questions, and please check out the paper. Yes?
It seems that your result could apply to other targets than proportional, right? Could you replace the proportional target by any function that goes from the populations to the seats and adjust ex-ante proportionality and quota?
Yes, yes. There's nothing specific. Like in some sense, like this proportionality is always proportional to the share that we want, and the way I'm thinking about it is that this is proportional to the population, but you're entirely right. You could, for example, have a square root function or something like this. Yeah, that's a good comment. Yes?
So in all this, it takes the number of seats in the legislature as fixed
yes.
in size, but it's not obvious that like an instance that was somehow hopelessly difficult to handle could get easier if you added one seat or two seats. As in, if you view that as a variable change also. Is there any sort of case where people look at that dimension?
I think typically in apportionment you treat the house size fixed, and I think in most countries as well. I happen to come from one where the house size is not fixed before the election, but in most countries around the world, like the House here has 538 seats. I hope I'm not embarrassing myself. So typically I think people take this for granted. But you're right, if you have flexibility in the house size, you can make things more independent, and that would definitely help. Here, I don't think we end up needing it. And I don't think it would help, for example, with the impossibility that we show, because this is orthogonal to the randomness. But in general, I think this is a very good point. Yes?
This is a comment.
Yeah.
It seems like there is a hidden axiom where after dividing the seats, they must remain fixed, the static. But there are countries in which parties can merge, and actually they divide the time between themselves to avoid these things.
This is the first time I hear about that. Yeah, please let's talk offline. And yeah, maybe I think the next speaker is Sarush.